I know, I hear it all the time. Thought it was supposed to be something more complicated than that. Yeah. Okay. Now it's guilty of the same thing. So, so the moment about the xy plane, what you do is instead of integrating just the density to get the mass, you're integrating the density times the distance from every point in the object to the xy plane, whatever you're computing the moment about. So this is what you integrate. Similarly, you want the moment of the object around the xz plane, that's this plane right here. Not that waving my hand like that really accomplishes anything, but hopefully, I don't know, maybe like one of those people on a game show. Here's the plane. The distance in this case would be y. So, and it's going to be, oh, that's a terrible line. There's this illusion of orthogonality to this. So mxz, triple integral of y times the density. And then finally the moment around the yz plane is x times the density. And this is a signed distance, meaning it's allowed to be negative. So if the object was over here, for instance, y would be negative, so the moment around the xz plane would be negative. All right. So once you have all this information, you've computed the mass and you've computed these moments, then you can come up with a center of mass. So x bar would be the moment around the yz plane divided by the mass. Okay, so over E, putting that in all of these. So what if the density was constant? Well, if the density was constant, it would be some constant rho, but you could pull out, and it would cancel out because you have it above and below. So it's like you would be getting the average x-coordinate of all points contained in the object. Similar for y bar, so that would be mxy, sorry, xz rather. So triple integral of y times the density over the mass. And then finally the z coordinates, you would get mxy, moment around the xy plane, over m. Okay. So with respect to the weight given by the density of the solid, it's again like an average z coordinate in a sense. Right. Okay, so, and these formulas just are direct generalizations of formulas that you learn in physics for simple systems where you're working with moments and computing centers of mass for a case where density is not a concern because if it's assumed to be uniform. So that's what these integrals do. They provide a way of taking formulas like mass equals density times volume, formulas involving products, just like area is equal to width times height, and allowing you to generalize those formulas to cases where the quantities involved are not uniform. Okay. And I skipped over where this is covered for 2 dimensions. So for a 2-dimensional object, if you have a flat object, also called a lamina, the center of mass, x bar, y bar, is the point at which you can balance the lamina horizontally, like on the tip of a pencil, for instance. So that would be the moment around the y-axis. So there'd be double integrals involved. Let's call this lamina d. So again, you're integrating x times the density over the integral of the density. So this is a two-dimensional analog of what I just talked about for the center of mass. So it's the same idea here in 2 dimensions. All right.
Down there on the
Yeah.
on y, the denominator doesn't have to be d. Is there a reason?
There should be a dm here.
It looks like the thing was wiped out.
Oh, okay. All right. So these are certain uses coming from physics for both double and triple integrals. You can also compute, for instance, the moment of inertia. Okay.
What do you mean by moment?
So the simplest case of a moment involves trying to, I'm wandering out of my comfort zone here, but like take a seesaw, for instance,
Okay.
and where you want a seesaw, at what point should a seesaw rock on to be balanced when you have people of different weight sitting on either side of it. So it's basically about trying to represent an object by a similar object that has all of its mass concentrated at a single point. As far as why it's actually called a moment, why that word is used, I couldn't honestly say.
Okay.
But it comes from having all these forces balance one another.
Okay.
The moment of inertia, also called a second moment, is used to indicate an object's tendency to rotate around a particular axis. So for instance, in the three-dimensional case, now here the moment is given by the letter I and a subscript of x. So the moment around the object on the x-axis is a triple integral of the other variable squared, y squared plus z squared. See, because here we wanted the distance from any point in the object to one of these planes. Here we want the distance from the object to a line, the x-axis. So here, this is a distance, and there should be a dv here, of a point x, y, z to the x-axis and squared. Okay. So the interpretation of this quantity Ix is the tendency of the object to want to rotate around the x-axis. All right. Okay. All right. Now, given a triple integral such as this, of course, how are we going to evaluate these kind of things? If you have any old region, or really now it's going to be a solid E, how are you going to set up the integral in order to be able to evaluate it? So one example of this would be, for instance, a tetrahedron. Let's suppose we have